Thanks to everyone for joining this session. So today's session, as always, had been the case with the previous release updates. It is a little bit busy. So today I'm going to start with some new enhancements on NVHD side with respect to deterministic optimization and sensitive parameters filtering. And I'm going to present a very interesting case study with the customer in which they use this optimization workflow to optimize or achieve their NVH responses within target. So this is something which I'm going to present today. And then once the NVHD feedback is done, the last item related to Steam enhancements and application case study will be covered by my colleague Uma Mahesh. So not wasting any more time, I'm just starting my presentation. So the first thing that I'm going to do is to talk on deterministic optimization in NVHD Classic. So as far as NVH optimization is concerned, there are a few topics like what is optimization, what is deterministic optimization versus RBDO, what are the different type of NVH optimizations which are done, what are the user interest, and what are the attributes for NVH optimization. So these are the points which we are not going to cover today because all these points were covered in detail during last webinar for 2022.1. So in the previous webinar of 2022.1, we had seen that in the Unity framework, we had introduced a complete seamless and integrated workflow for optimization setup and results processing. And this was available only in Unity. So with this setup, we did give this demonstration to many OEMs, and we got a lot of positive response, a lot of positive feedback from the OEMs who saw this workflow. And specifically from JLR UK and Mahindra India, they were very impressed with it. So Mahindra India started the evaluation of it on the Unity version. And this is the case study I'm going to present later in the presentation. And this to evaluate this workflow was the only reason for them to use the Unity platform. So they got exposed to Unity platform while evaluating this optimization workflow. JLR UK is still on Classic platform, and there are no timelines which we are sure of for them to move to Unity. And there was a request from them to introduce this optimization workflow in Classic. So this was one of the reasons that we introduced this workflow in Classic also. And then there were some enhancement requests from both from JLR as well as Mahindra, and basically two main enhancements which we were able to deliver were to link the design variables and to define mass and volume as design responses. So I'm going to talk a little bit in more details about them. So as in Unity, we have introduced this optimization workflow in NVHD Classic also, where you will be able to define design variables, define design responses, derived responses, constraints, objectives, and create and solve the OptiStruct run from the Classic NVHD version. It is also possible to save this complete setup in the assembly XML for reuse, and we have also introduced the post-processing functionality. So basically, whatever is available in Unity for optimization workflow, all those same things are available in Classic also, but with little bit different workflows. So as far as the implementation goes, it is again a part of the analysis manager. So you will see that this is the analysis manager window. You can select analysis, define it, apply it, and then this new option of optimization will get activated, and you will be able to define your optimization setup after by adding it. So the first option is to create the design variables, and you can see that whenever I click on the option to add the design variables, you can add properties or materials or NVH connections or modal parameters as design variables for materials and properties instead of going through Design Explorer workflow, we are going through HyperMesh panels. But this is the only change here. But as far as populating these design variables, specifying the lower bound, upper bound, and all those things, it is pretty much possible in Classic also. Once you select the design variables, the next step is to create the design responses. So even here, the workflow is kind of similar. From the NVH response point manager, we do populate the responses automatically. And once these responses are populated, user can specify the request, whether they want to define the response for mean, maximum, RMS, RSS, specify the frequencies, specify the scaling, and specifying the load case. So user can complete their design response definition part here. Then there is an optional step to create the derived responses, and here the workflow is same as Unity. The next step is to create constraints, and here the user can create the constraints, and instead of Design Explorer guide bar, you will see the HyperMesh panel here to create the constraints. The user can create the constraints and then to specify the bounds for lower bound as well as upper bound. User can specify the absolute values, or they can also specify the bounds using curves. And the last step is to create the objective, and here again the user can select the objective or select the response for defining the objective, and different type of objectives can be specified, like minimize or maximize, min max or max min. So once all these steps are done, then the next step is to write out the solver deck for optimization. So this is just a short video showing all the steps. We will just go through it fast through it. So you can see that user can define and apply an analysis. And what happens is this new option of optimization gets activated. You can check it on, and you can add the design variables. So here you can see the panels, and user can go and select materials or properties as design variables. You can also add connections here or modal parameters. And it is also all these lower bound and upper bound, these are editable. You can change the bounds here. Once now you can add also the connections. So all the different type of design variables which were available in Unity, they are also available in Classic. Here user has defined some materials and some connections as design variables. The next step is to go to create the design responses. So all these design responses are automatically populated from NVH response point manager. User can specify the request type. The complete list is available. So depending on the request type, the user can also specify the load step name here. User can specify the minimum and maximum frequency for each design response, and also can specify the scaling. So once it is done, then the user can go ahead and create a derived response from this panels. But we are not going to define any derived response here. The next step is to create constraints. Here user can select the responses for which constraints needs to be specified. And user can specify the bounds in terms of absolute values or also in terms of curves. So once constraints are defined, then the next step is to define objectives. So here user can select a response to be defined as objective, and I have select to minimize the response. Once it is defined, then the next step is to click on the optimize button and create the job or the solver deck for optimization. So this is the workflow on the pre-side, which is almost on similar lines as Unity. So if you have any customers who wants to evaluate this workflow on Classic, 2022.2 is the version for them. Now the next part is about the post processing. So we have introduced a dedicated post-processing utility for deterministic optimization. In this dropdown, you will see that for optimization, there is the option of deterministic. Here, users can read the result file. They can review the optimized variables, basically compare baseline design variables versus optimized design variable values, and also can view them graphically. So this is just a small video showing the implementation. So in this dropdown, you will see a new option for deterministic optimization. User can select the punch file from the optimization run, load it, and when load the response. So the red color curve is baseline response, the blue color curve or cyan color response is after optimization. User can see or review the optimized variables. They can also plot and visualize the change in the design variables graphically. So this is the implementation on the post-processing side. Now, there were some enhancement requests in this optimization workflow, as I mentioned you at the beginning of the session. So let me give you a little bit background about this. So this is the baseline and the optimized response, which you will get or which you should expect at the end of optimization. And if you look at the results, the optimization results, they are looking good, right? I won't think that there will be any user who would be unhappy with this output from the optimization. But the important question is, are they acceptable? Or will the users accept? And what is the general practice for acceptability? Because just by looking at the responses is not the confirmation that users are happy with the optimization output. And let's have a look at it. So these are some of the design variables which were used for optimization. This is just a very short list just for the representation. So there were many other design variables used. So if you see all the symmetric design variables, for example, engine mounts, LCA mounts, rear LCA mounts, some thicknesses, for example, wheel arch on the LHS and RHS side, B-pillar outer panels on the LHS and RHS side, they all have these all symmetric parts have same values, right? And we gave this for optimization, and these are the optimized values. And you see that the values on the LHS and RHS side have changed. So for few of them, it is increased. If it is increased, they are not the same. For few of them, it has decreased. For example, front LCA, the value is decreased from the baseline. And for RHS, it has increased. So basically, the relationship between design variables is not maintained after optimization. So it violates the practical constraints, and hence this is not acceptable. So this is, even though the reduction in the results is good, but the values which got optimized are not practical. So what is the solution to this problem? So the solution to this problem is to link the design variables. So in OptiStruct, you can create a link between design variables. So you have two cards, D-link 1 and D-link 2. So here you can basically create relationship between different design variables. You can define one design variable as a dependent, second design variable as independent, and you can have some multipliers and coefficients. So and you can have multiple D-links. So for example, if you want to create a situation where stiffness in X direction for one mount, or let us say LHS mount, should be equal to RHS mount, then this is how the D-link card needs to get created. You can also create some more complicated D-links, like want to maintain the stiffness in a particular direction or more than twice of in the X direction. So such kind of equations you can create. And this is the solution. So what happens is by introducing these D-links, we kind of maintain the relationship between the design variables, and at the end of the optimization, what we see is that all the linked design variables, they change in the same way to achieve your objectives and constraints. So this is a very important practical consideration, and this is what is implemented in .2. So this is a very good implementation. So what has been done is in the design variables tab, there are right click options in front of design variables to link or delink the design variables. And once the design variables are linked, there are options to specify the constants, constant multipliers and coefficients which get used in the delink card definition. And then there are some smart logics introduced to avoid user errors with respect to, for example, if some design variable is defined as an independent variable, then it cannot be defined as a dependent variable and vice versa. And also multiple dependent variables can be defined for multiple independent variables. So uh, these logics are important so that user don't end up in doing the mistakes. And at the end of the day, what we do is we export the solver deck with necessary delink cards. So this is the implementation. And by the way, we use this implementation in the case study that I'm going to show you. And the next implementation is to define the mass and volume as design responses. And this is very important enhancements and very much used by the OEMs for their value engineering phase, where they want to do some mass reduction or they want to study some weight evaluation proposals. So now, in addition to velocity, acceleration, displacement as the responses, we can define mass and volume also as the responses. And then you can track the mass of particular components, mass of particular subsystems, or mass of the complete vehicle also. So all those things are pretty much there now. So these are the two enhancements in the optimization workflow. The next important enhancement which was done was for sensitive parameters filtering. We know, and we have spoken about it previously, that these are the important steps in the optimization. You have to select or define a load case, define responses, define design variables, define objectives, constraints, and then submit the optimization run. So these are the main steps at a very high level. And the success of the optimization, no doubt it depends on how do you define the objectives, constraints, and design variables. But the very important factor is how do you define the design variables. So whether your optimization will be successful or not, to a great degree, it depends on what kind of design variables you define. So basically, it's very important to understand and decide which parameters should be defined as design variables for optimization. How do you identify them, and what are those typical design variables? So which parameters should be used for design variables for optimization are the ones which are sensitive or contributing parameters for that response. You can imagine that if you consider a full vehicle case, you can have thousands of design variables which can be used, but for optimization you need to use only few ones which are sensitive. And how do we identify them is by doing different diagnostic methods like modal contribution, TPA, DSA. But the most widely used one is doing the design sensitivity analysis. So the important thing is to identify your design space for optimization. And typically this is done using design sensitivity analysis. And what can be those are like those can be thicknesses, material properties, connection stiffnesses, damping, and modal parameters. So what is the typical workflow to identify these sensitive design parameters are like you will plot your responses and identify the concern frequencies which you want to take below the target. And for those concern frequencies, let's say you will define the design variables. So I'm just putting some rough number here. Maybe you will define some 2000 design variables and put and submit the DSA run for concern frequencies using OFreq or by using pcut. Once your sensitivity results are out, you kind of post-process the DSA results and identify the sensitive variables. Maybe from the list of 2000 design variables, you can identify a list of reduced variable. Maybe it can be 50 or 100, but you will get a reduced set of sensitive variables. And then use these sensitive variables as design variables for optimization. So this is the typical workflow. Considering this need or this workflow, what we have done is in the DSA output request in the analysis manager, we have introduced this workflow in which you will be able to select the design variables in the same way that you are able to select in optimization. So now here users can go in this analysis manager, and in the diagnostic section, user can define the responses, and user can also define the design variables for which the DSA needs to be done. And once this is done, user can write out the solver decks for the DSA. And this is a very user-friendly way to create the job or solver decks for DSA. So this is the new enhancement or implementation. And once the runs are over, so in the DSA post-processing utility, we have done the enhancement in which user can load the sensitivity HTTP file, result HTTP file. The user can plot the response. He can select particular frequencies or concern frequencies and plot the list of sensitive parameters. And once those sensitive parameters are plotted, there is a new option introduced here where you can write out these design variables in an external CSV file. So you can just imagine that you have now a list of 10 bar plots for different responses at different frequencies. You can pick and choose what you want to write out in the external CSV file. So you will write out a CSV file with information on those sensitive parameters. And then this CSV file can be used in the optimization area in the design variables section. You can read this CSV file, and all your design variables will be fetched in and populated from this CSV file. So no need of manually selecting. So now you are very sure that the results or the sensitive parameters can be accurately predicted and used as design variables for optimization. So this is the complete workflow on sensitive parameters filtering, where we have enhanced the DSA pre-processing side, DSA post-processing side, and kind of introduced these enhancements on the optimization side also. Now, along with this, there are a few enhancement requests, and one of the major enhancement requests is to define the response constraints and objectives directly from the result file. So today what we do is we have to study the responses and key in everything manually. So this is something which they are looking forward to, and I'm going to start. Basically, we spoke about it, Ira and myself and the Design Explorer team. We spoke about it. We'll see if we can do something for this in .3. And there are a few more, like we want to update the assembly XML with optimized variable values. We want to do some enhancements in the visualization of design variables. And there are some things that we want to do with respect to defining the modal parameters and connection parameters as design variables by directly from the network view. So these are a few of the enhancements that you will see happening in near future. So far, optimization workflow is receiving very good feedback, and it is turning out to be a good enhancement. The next important point is about the NVH process manager to migration to ESG process manager. So this is one of the work or a major development effort which went in .2 timeframe. And the idea was to improve the performance of these process managers on Unity, to remove the Java dependency. And this is a major enabler for easy migration to new customization platforms like Pulse. So we completed this complete process manager migration to ESVG process manager in .2. And this was basically a very good development effort, and now we see that in Unity the process managers are kind of sleek without any performance issues or delays, and it just works smoothly. Now there are a few points that I would like to talk on the NVHD post-processing side. So we did some good enhancements. And those enhancements are majorly in the modal FRF. So here we introduced 3 major enhancements. One of them is on-the-fly conversion between different response types. So you'll be able to convert displacement to velocity to acceleration or any other, and vice versa on the fly. I will show you a video how it is implemented, and also on the fly calculation for the derived quantity. So it is normally a request that for a given frequency range, users want to calculate RMS, RSS, or average for that particular response. And then in the modal FRF now it is possible to define the multiple subcases. So these all enhancements we did as a response to compete against LMS Virtual Lab. So we are involved in a benchmarking activity with the Hero Motors, where the idea is to replace Siemens Virtual Lab basically. And these enhancements were done to win that benchmark. We are making good progress. So let me show you a few of them. So this video will show that in the modal FRF utility, this response is plotted, and you will see that there are once the response is plotted, now there are right click context menu to convert. So we know that this response is plotted in velocity, and there are right click context menu options to convert it from velocity to acceleration or velocity to displacement, or even to invert that response. So I have just converted this from velocity to acceleration, and you will see that now you have easily converted it. Now there is option for derived quantities here. You will see that in the right click context menu there is option for derived quantity, and you will see that you are getting the values for RMS, RSS, average, and area under the curve, and you can specify you can choose the frequency range, starting point and end point. So I want to see the RMSs from the values from 150 Hertz to I think 300 Hertz. And you will see that for this selected frequency range, we have it is automatically calculating the RMS, RSS, average, and the integral, or basically the area under curve for these curves. And it is also possible to turn on and turn off these values on the fly. So basically, if you don't want to see integral, you can just turn it off and that value will go away. You can bring it on, you can turn on, turn off, whatever you want to do with this. So this is the kind of enhance, and you can change the frequency range, and you will see that these derived quantities will change on the fly. So this is something which was one of the enhancement requests, and we have seen that this was happening with virtual lab. So we introduced this, and at least Hero users are pretty happy with this implementation now. And you can take advantage of this, and to calculate these derived quantities or conversion, this is also possible in the integrated diagnostics. The next enhancement is to define the multiple subcases in modal FRF. So till 2022.1, we were able to define only one subcase, but now we have introduced for general case, we have introduced a subcase column. So where you will have two subcases. So you can define the multiple subcases. You can specify the excitations. I'm reading the CSV file for excitations. So I can assign the loading strength, which I have created by reading the CSV files. And I just say apply. And the punch file, now the next step is to define the responses. I have defined two responses here. And I'm requesting velocity as the output, specifying frequency range of analysis. When I calculate, so I can calculate or export out the punch file. And you will now see that there are two subcases. One is subcase 1. And this is just a validation that the results coming from modal FRF and the OptiStruct are matching line on line. So basically, there are two subcases, subcase 1 and subcase 2. So in the subcase area, you will find two subcases. So this was also one of the enhancement that we did as a competition against virtual lab. So these are all the changes which we have introduced in NVHD, starting like deterministic optimization, linking design variables, defining mass and volume as responses, then sensitivity parameters filtering, case study with the optimization workflow, and some enhancements on the post-processing side, along with process manager migration to ESG process manager. So these were the work in .2. Now I will pass on the presentation to Uma, who will take or who will talk about the enhancements on the Altair SIEM side. Uma, over to you.
Thanks, Azar. Hello, everyone. As you know, we started working on converting SIEM into Unity platform. So in last releases, we have introduced the basic workflows for creating of SEA subsystems, SEA excitations, SEA connections, defining noise control treatments. Now in this .2, we are working on to improve the overall workflow as well as make it easier for user to create the subsystems, which is very typical from normal FE mesh building. So to enhance these capabilities, we started working on symmetry option, in which you can symmetry the whole SEA subsystems along with the subsystems. If any connections are defined in between those SEA subsystems, as well as any noise control treatments defined on NCTs will be carry forwarded into the symmetric side. So as you can see here, you can select all SEA subsystems and you can select a plane. So if you even select SEA subsystems, it will automatically, if the junctions are defined between two subsystems, it will automatically understand them. Then it will start reflecting them and the connections, as well as the intricate details and the advanced options. If you have defined on one side, all will be exported to the other side. In this way, it will be easy for the user if he even creates a half subsystem and define all his noise control treatments and then reflect it. The whole properties and everything are copied properly into the other side. As you can see, the area details and all are converted, and the advanced options of defining NCTs and are also updated. So this is one of the major works which we did. The next major enhancement was to have a common saving mechanism between low frequency and high frequency. We started working on file saving mechanism, in which now we are able to export all SIEM entities, including the SIEM entity parameters and the FE geometry surfaces which are used to create this SEA subsystems can be saved and then re-imported into the session. This is one of the critical projects for us because this will be further used and integrated and will be used in creating a critical for integrated workflow, in which it will be merged with full frequency full vehicle in NVHD XML. So in this way, a user can have a common XML in which both low frequency and high frequency model coexist, and it will be easy for the user. So the next major project was few customers whom we are interacting with has a request of adding measured inputs into the system. So typically, as noise control treatments or sound packages are majorly coming from the vendors, so they have what typically vendors are doing nowadays. They give the effect of the sound package in terms of transmission and absorption in through the actual measurements from the experimental data. So user wants to add it on top of SEA subsystems so that this can be used in further analysis. So previously we had an option to define noise control treatments only in terms of layers. Now we have enhanced it so that they can add the treatments in terms of measured absorption and transmission loss, which is the outcome of our normal NCT definition. Then these are the major activities. Apart from that, we did few user enhancements uh, in a smaller sense. So as seem especially for automotive industry is all about airborne noise, it is critical to give a user some options to create cavities easily. And before we had an option of creating only an entity which is closed to create a cavity. Now we gave an option using a similar drag option from HyperWorks Unity. We integrated in such a way that you can create SEA subsystems using drag option, and in this way he can easily create SEA subsystems, both single and multiple cavities based on user need. So this is one of the important features for user because it will help to create cavities easily. Further, we are going to enhance it to create to extend it onto a single plane so that yeah, the surfaces are neat, and it is very useful when we are creating exterior surfaces. That is the next enhancements which we are working on. In this way, you can see that the cavities are created. You can see the cavities and the subsystems. Uh, the next enhancement is while generally the current workflow all competitors and we have is use FE as well as geometry to create SEA subsystems. So for that, you either do it automatically or you select a nodes in such a way that it creates a subsystem. So for example, if I want to represent the whole roof, I need to create a subsystem in such a way that by picking the nodes or surfaces, you create a structure. But while doing this, what happens is as Seam doesn't know what is the parameters of properties and material details of this, user has to define this mundane activity repeatedly. So to avoid this, what we did is we come up with a smart feature like it will automatically read the OptiStruct or FEM files and NASTran files, and it will automatically, while picking the nodes, it will select the nodes. From the nodes, it will select the component. From component, it will try to identify which property and material is used, and it shows the user uh, based on the picked nodes. In this use case, he has picked. If you see here, uh, he has selected nodes, one on the floor, one on the seat reinforcement. So because there are two components or two parts which are being used, it throws a message of showing there are two components which are available and which thickness you want to use. So based on that, user can visualize it and select which one is important for him. And if it's a single thing, for example, on the roof, which I'll show you now. So if you select it, it will automatically update the properties because it's made from a single part. It will automatically update the subsystem details of properties and materials directly. So user doesn't need to specify these details. So in this way, we are using the OptiStruct features, uh, details which are already available with us. Further, uh, one of the one of the important user enhancements which we did was when we were applying noise control treatments onto the SEA subsystems or for example, or on the floor. What used to happen was this NCT definitions are identified with respect to junctions. It has to be translated into junction. So what was happening was there was a lot of confusions to the customer as well as the AEs. What is exactly getting converted for the noise control treatment? So to understand it, what we did is we gave an option. We introduced realized noise control treatment concept in such a way that whatever treatment is applied, it can be realized on the SEA junctions. So even on the SEA junctions, user can see what NCT definition is applied on that junction. In that way, he can understand how the energy and what kind of treatment that particular junction has obtained from the plate. Uh, and the other thing was user defined transmission loss. So the problem is when if user wants to update a measured TL curve directly on junctions apart from user defined NCTs, what was actually happening was we need to delete the current junction and create a new acoustic junction and then apply the measured transmission loss. Because the transmission loss come is working between two acoustic cavities, which has the information of the plate inside. But this is kind of overkill because you have to delete a junction, then recreate manually one junction, and then add measured transmission loss. So to avoid that, we gave an advanced option inside the structural acoustic connection itself, so that you can define the curve and it will automatically deal all the conversion of structural acoustic connections into acoustic connections, and then update into the corresponding acoustic connections. So this were the enhancements which we worked on dot 2. Further, we are working on uh, improving NCT creation, and further some requests which came from GM and Rivian is what we are targeting for Rivian, apart from integrated workflow. So these are the major projects for dot 3 which we are targeting on. And few of the AEs, I had a question like when and why to use seam, how to use seam, what frequency range to use. So to explain this, I took a simple example so that most of the AEs are present here. So just to explain, if whenever you are doing an OptiStruct run and trying to solve any engine excitations or road excitations which you have applied, uh, the whatever interior cab noise which you are hearing is purely because of the structural transfer and the components inside the cabin which are vibrating. This is what an OptiStruct can predict. And once you apply acoustic sources and once you add Bayard parameters, you can solve the airborne also. But in using seam, you can also quickly do airborne analysis. For example, if uh, because of tire rotating, you get tire horn noise or the road noise because of the tires, uh, or the engine combustions which propagate through the air inside the engine bay region, which transfers inside to the cabin, just like if you talk in one room you will hear in the other room, even though there is no vibration, it gets transferred. This is because of the mass law transmission. So this is a major path for airborne transfer. So to solve such problems, you need to use a seam which can help you to solve till higher frequencies, because generally the airborne propagation happens at higher frequencies. So that's why most of the times we solve the low frequency problems with OptiStruct, and we tend to use seam for solving high frequency problems. Whether it may be wind or tire horn noise or engine bay noise, both airborne and structure borne, you can be used for seam. So in a sense, what you hear is the effect of both. But if you want to quickly solve the airborne noise with minimal effects at higher frequencies, you can use seam directly. So just to give an example, how we can use for subsystem analysis to start to understand seam, what you can do is, if you see, if for an engine bay problem or for engine excitations which are coming from the engine bay, the dash is a major airborne path from which the energy transfers. So I took a dash as an example and I created dash in seam in high frequency. Then I created cavities across it, um, across the dash as a source and receiver, representing the acoustic cavity inside the cabin as well as the engine bay region as a source. So once I have apply the source in the engine room. So once you do that, you get a basic you get the basic transfer of energy which is happening. And at component level, to start with, we can quickly check how much transmission loss is happening because of the bare panel. So, and once you do that, you can even check if I change the thickness of the components, how is the effect. So basically, I took a dash, I created a source and receiver. I did a transmission loss for a baseline in which the thickness is, let's say, 1.2 mm. This is the transmission loss effect of the dash without any NCTs, noise control treatments. Now on top of that, I quickly changed the thickness from 1.2 to 2.4. What is the effect? So from here, it feels like the transmission loss is happening good at low frequencies. But if you see from 1250, 1600 to 6300, there is some deterioration at the higher frequencies. So it may happen that this may be useful or not useful, because considering the weight. I'll explain it more for further analysis. Now what I did is I tried to increase the damping effect of the panel of the dash. So I made it from, for example, from 0.02 to 0.04. And you can quickly check what is the effects of the improved damping loss factor. As you can see, the effect is very minimal at very minimal at all the frequencies except at higher frequencies. You can see some change. Similarly, what I did is I changed the material. So just to show you why for higher frequencies aluminum is a problematic region and why we tend to not use aluminum. So I just showed an example. So for a dash, I just kept the same thickness and I just changed from steel to aluminum. You can see that the transmission loss almost deteriorated by 5 to 6 dB by just changing from steel to aluminum. This clearly shows that the density, because of the lesser density, the more energy of sound energy is entering into the cabin. So in this way, you can do some quick studies and understanding how you change the panel behavior, what will be the effect of it. These are the few examples. You can add a stiffener and see, maybe add a stiffness multiplier onto the panel and see what will be the effect at different frequencies. And this way you can understand how the dash itself can be improved. And you can do some quick as a component level, you can take a quick decisions on what material to use. Further, now on top of it, what I did is on a same dash, I have applied a noise control treatment of absorber and barrier. This just as a noise control treatment of just two layers. One is the foam an absorber which absorbs the material, and one is a barrier EPDM layer which blocks the noise which is coming on, which blocks the noise. So now for the same dash, when I have applied a dash, you can clearly see that there is a huge improvement in terms of transmission loss. So it tries to obstruct as much of energy which is entering into the cavity except at this region. This is due to the mass being added. So this clearly shows like how you can do simple analysis and try to understand seam as well as explain to the customers. So to show you the overall thing, so you can see that just all this runs I can complete in just half an hour. So this is the advantage of seam. um, and in even full vehicle level also, the solver time is very less. But this shows that we can take a quick information out of seam analysis till higher frequencies without losing any correlation, which maybe there's another concept of how many modes in bar band. So based on that, you can decide on this information and you can take a decision. This way you can start understanding seam. So, and the solving time is very less even for the higher frequencies. And so this is a simple example how you can use and try to understand and explore the seam. All this we have a tutorial also if you want to explore. That's all from my side. Thanks, Evan.